And welcome back. This is our second chat on our reaction rates. And this is kind of distinguishing between reaction orders. And I'm going to show you guys some of the math on how to get it with our initial rates method. So we have an individual and overall reaction orders. And so we'll get a chemical reaction given to us. In this case, we have this nice balanced chemical equation. But our reaction rate law in this case is also given to us. And this guy right here, this is the important one to look at. So even though we know that we have a balanced chemical equation and like, oh, look, we're reacting two gases together, we're going to get that nitrogen monoxide to turn into just nitrogen gas and water. None of the information that's in that is actually going to be what we're talking about. So it's all on the rate law side. And you'll see that we have actually, I should include rate. Rate is equal to K, that's some constant, the concentration of nitrogen monoxide squared times the concentration of hydrogen. And when we're reading this, when I was talking about orders earlier, what we're saying is that the rate of this reaction is going to be, we'll say, second order with respect to NO, and first order with respect to H2, and that is third order overall. Where we get these numbers from, we have our NO, and we have that squared there. So write that 2. That's where we're getting the second order from. First order is going to be with respect to hydrogen gas. And there's nothing there, but you can always have an invisible 1 in your head because anything raised to the first power is itself. We call this the identity. And so we don't write them in because that would just be a bunch of ones to have to write in all the time. But so if you don't see power, it's just first order. If you see another thing, it's second order in that case. And the third order is we combine them, we just add them up. Second plus first, that's going to equal 3, right? So we're good on that guy. Now, with these, the key at the bottom is that we don't look on the reaction. The balanced chemical equation doesn't have anything. What we really have to do is we have to do some experiments. So we're looking for experimental data so that we can figure out what the reaction orders are. They might be given to us. In our first examples, we're just practicing the reading of it, but we'll talk about the experimental data too. So for each of the following reactions, we're going to use the given rate law. So we're going to look at the rate half of it and determine the reaction order with respect to each reactant and the overall order. So what we're going to do, we're going to look at the exponents in the rate law, not the balanced chemical equation. It's not that we're trying to distract students with the balanced chemical equation, but if we're talking about a chemical reaction, we need to have the balanced chemical equation there so we know what we're talking about. And then we're going to add together the individual orders to get the overall reaction order. And so we can take just the first one here and say, all right, we got this rate. We've got K, some constant based on temperature, times nitrogen monoxide squared, the concentration of, and times the concentration of oxygen. So when we're looking at that, our idea is we look at the exponents to find the individual orders, and we add them together. In this case, the exponent is 2 for that nitrogen monoxide, and oxygen has the invisible 1. So we'll say it is second order with respect to nitrogen monoxide, first order with respect to oxygen, and third order overall. The other two, a little bit trickier, but when we look at B, we have, it says it's 3/2 order, and let me put these lines in better for us. Yeah, there we go. So it has a 3/2 right there. We're just going to run with it. And I'm going to say like, all right, yeah, this is 3/2 order, even though we didn't talk about that at all. That's where that number's coming from. That is what it says. And if it says it in the thing, you just go with it. We're not questioning anything. Now the last one has a little fun trick for us, but we have our H2O2, that's hydrogen peroxide, is first order, boop, and our iodine iodide has first order also, because we have those individual ones, but we also had a little hydrogen in the balanced chemical equation that was not listed at all. So we have that aqueous hydrogen. It's on the reactant side, so it should be showing up here. But it is zero order with respect to hydrogen because it does not appear in the rate law. And if you remember zeroth order, it doesn't influence the rate, so it would have been just a ×1 sitting here, which would have been weird to write down. Like, why would we write ×1 into our, I mean, you don't write ×1 into things because it's unnecessary. So that's where that guy is coming in also. So now I've seen kind of how to read a rate law. And what I want to do is see how we get a rate law. And these are, let me erase those lines that I put in. This is how we determine our reaction orders for each individual thing. For just a general chemical reaction, doesn't need to be 2B, it could have been A plus B results in C plus D. Our rate law will have the form of the rate is going to be equal to some constant times the concentration of chemical A raised to some power times the concentration of chemical B raised to some power. And to determine the values of those two powers, that M and N, we do run a series of experiments where we keep one concentration constant and another one we adjust, usually doubling or halving it, depending on which way you're looking at it, so that we can see what the effect on the rate is. So this is just a initial rates table. So we have these things like in experiment 1, we have 2.5 times 10 to the negative second moles of A and 3 times 10 to the negative second moles of B. We have an initial rate, comes out, what is that, 1.75 times 10 to the negative third moles per liter second. So not terribly fast compared to everything else. And what we end up getting is we'll get our rates and we'll keep these two guys constant, while between A, we double the rate, and then we look at what happened to the initial rate there. There is a really simple algebra method for this, but it tends to make everybody batty when we look at it. So when you look at this, we have what we're really getting on this is we have rate, the second rate, divided by the first rate should be equal to the concentration of A at the second time divided by concentration B of the first time to the power of whatever it is. So when we're starting to cancel things out, concentration B was kept the same through those first two, so we get to cancel that out completely. In concentration A, these K's are in the rate law. And I should say what this really is rate law 1. And then we are going to divide it by rate law. I should have wrote law in there. It's rate law 1 divided by rate law 2. And we just took it apart on each side. When you cancel out everything that is the same across each incidence, what we get is just, it is the second A divided by the first A, both raised to the M. So we can pop that out and we just get A2 divided by A1, both raised to the N. And when we look at it, it's 3.5 times 10 to the negative 3. You know what? We can even cancel out the 10 to the negative 3 on each side, or on top and bottom, because it's going to be the same. And it's going to be the same there. So what we're really looking at is 3.5 divided by 1 3/4. That's 2. This 5 divided by 2.5 is also 2. 2 raised to the M power, because we still have that M right there. That guy's what we're looking for. Now, this comes out to be very easy. M equals 1. We didn't have to go through all of this math. And if the algebra part of it is daunting to you, don't worry, you're in good company. The other method that I use on these is that I look here and I am going to compare two different. I'm going to look at this guy. If these two are held the same, great. In this one, I'm doubling. 5 is twice 2. I just look at this. Is 3.5 twice of 1.75? So I can say 1.75 times 2 equals 3. If that is true, it is first order. If it is not true, it won't be first order. But you'd pretty easily tell. And it's a little harder with your other concentration just because of the way that we wrote this, because we're going to have to look for something where we have the same numbers here and then different numbers here. So I'm comparing, a little bit further away, but this would be, it's the same thing because it's 3.5 and 1.75. These are idealized sample numbers. But even if we took the other one, you'd say like, is 7 twice 3.5? Because we have our initial being 3 here, 6 here, 5 and 5, and you can compare those. And it's good to have those 2 points of comparison. So this is a perfect, easy way with sample numbers. If we take a look at some real numbers, what we get is the same thing. And we can do the math problem, which is not that hard, but it does freak people out in the beginning. But if I have my nitrogen monoxide held constant for those two, I'm looking at these guys, 1.1, 2.2, it's double, that's easy. And my question becomes, is 6.40 double 3.21? This is a little bit of a trick because 3.21 times 2 is not 6.40, it's 6.42. But that's close enough. I mean, if I'm measuring stuff, there's measurement error all the time, and these would be real numbers. So I would say close enough. And then we would say it's a first order with respect to O in this case. Let me draw a first order up there. Boop. So first order with respect to our oxygen gas. Now for this nitrogen monoxide, I'm going to have to say, all right, I need to find where we're holding the oxygen constant, like these ones, and there is a doubling, right? Yeah, 2.6 to 1.3. Now these numbers, if it was double, it would be 6, but instead it's 12.4. So it's not first order. And let's see, 3.21 times 4, is that about 12.48? Oh, that's not times, Fleming. You got to fix that. It's weird trying to do this in white because I can't quite read what I'm typing out. I mean, like 3 times 4 is 12. And so we're close in here. So what this is going to look at is this is pretty close to a second order because when we double the concentration, the rate has suddenly quadrupled on us. And just comparing on the chart works out pretty easily for most people. You also have the math version where you compare the experiments where NO is kept constant but oxygen doubles. You write out your math for it. And I got to put in these fraction bars because they disappeared on us. And you are getting 1.99 equals 2 raised to the m, or 2 equals 2 raised to the m, more or less. So we could say m is 1 and the reaction is first order with respect to 1. And again, it looks like a lot, but you get to cancel out most of your rate loss. So all we're really doing is rate 1 divided, or rate 2 divided by rate 1, and then looking at our oxygen levels to find our M value. For the second one, this actually comes out pretty easily. But you can just use the log button on your calculator to double check that you have first order with respect to O2. So you have log A divided by log B, which will come out to 0.993. Finding our experiments 1 and 3, where we doubled the nitrogen monoxide, we get a similar thing, and dividing you get 3.99 equals 2 to the n. So this is where I was saying it looked like it was quadruple, not double. So we kind of did this all in our heads, and looking at the algebra again does bother some people. But you can also do n equals the log of A divided by the log of B, and that'll give you a 2 also. So we get our reaction is second order with respect to NO. And I know it just got dropped on you right here, but this log thing, if you don't know, it is a button on your calculator that we can use. It's normally covered in Algebra 2, but it's been a year this year, so I don't know if we've gotten there in everybody's class. Now that is just a little review on what we did to find our reaction order with respect to different chemicals by checking our concentrations and the initial rate. And I hope you learned something today.